Good morning once again, my dear students. This is Sir Mike. Today we're going to look into another process of finding the integral of functions, and that is integration by partial fractions. So the objective of today's lesson is for you to be able to solve integral of functions using integration by partial fractions. So to apply this method, let us first define decomposition in the mathematics. So here we have two dissimilar fractions, and if we add these two dissimilar fractions, we will definitely get the LCD. So 2 over 5 plus 1 over 3 is equal to 11 over 15. Now, decomposition in mathematics is actually uh, having the reverse of the process that I mentioned earlier. So we have instead 11 over 15, and we're going to look at the two numbers that will give us 11 over 15. So in this case, you have 11 over 15, and this is equal to a all over 5 plus b over 3. So in the previous equation, you know that a here is 2 and your b is 1. But in this method of finding the integral of functions using partial fractions, we will be looking, or we will be solving for values of a and b. Okay, so to apply that, let's have this example. So for example, you are asked to find the integral of 2 over x squared minus 4 dx. So at first glance, you will be tempted to use substitution in finding the integral of the function. Let's try solving the integral of the function using substitution. Okay, so the process is, of course, we're going to make use of an expression that can be substituted by u. So let u be equal to x squared minus 4 in this example, and we need to get the derivative of the function. So that is 2x dx. Unfortunately, the given the expression is only 2 dx, so we cannot just substitute your 2 dx by du because of the presence of the variable x here. So definitely your substitution is not applicable. So in this example, we definitely would like to use another method to solve the integral of the function. So in this case, we will be applying decomposition. Okay, so we write first your 2 over x squared minus 4. And then we will be looking at the factors first of x squared minus 4. You are aware that the factors of x squared minus 4 is x plus 2 and x minus 2. So the first factor will be the denominator of our first rational expression, and your second factor will be the denominator of our second rational expression. So we'll be having 2 is over x squared minus 4, and this is equal to a over x plus 2 plus b over x minus 2. Okay, so as I mentioned earlier, we are applying here a decomposition method. Okay, so we need to add a over x plus 2 and b all over x minus 2. So the LCD is x plus 2 times x minus 2. So we divide x plus 2 times x minus 2 by x plus 2. What is left is x minus 2, and you need to multiply that by a. Then you add, of course, b times x plus 2. You do the same process. You divide x plus 2 times x minus 2 by x minus 2. What is left is your x plus 2, and then you need to multiply that by b. Now, the denominators are the same. You have x squared minus 4, and definitely on the other side of the equation, you have x plus 2 times x minus 2. So the next thing that we need to do is to equate the numerators. So in this case, you have 2 is equal to a times the quantity of x minus 2 plus b times the quantity of x plus 2. Anyway, the denominators of the left and the right side of the equations are the same. You can actually equate the numerators. So we have this equation. Okay. Now, you need to solve for a and b. You need to solve for a and b. And how are we going to do that? You think of a number that will make the second expression b times x plus 2 equal to 0. Okay, in order for us to solve a. So in this case, we let x be equal to negative 2. And then we substitute the value of x in our equation. So you have 2, and this is equal to a times the quantity of negative 2 minus 2. You replace already your x by negative 2. And you have plus b times the quantity of negative 2 plus 2. This definitely will become 0. So negative 2 minus 2 is negative 4. So you have here negative 4a, and that's equal to 2. And your a here is equal to negative 1 half. Okay, you do the same with the next expression, that is solving for the value of b. So you think of a number that will make your a, or the first expression, be equal to 0. So in this case, our x will be equal to 2. So substituting x is equal to 2 to the equation that I mentioned earlier, this one, 2 is equal to a times x minus 2 plus b times x plus 2. You'll be having 2 is equal to a times, of course, 2 minus 2 plus b times the quantity of 2 plus 2. And the first expression, a times the quantity of 2 minus 2, is equal to 0. So you are left with 4b, and this is equal to 2. Hence, our b now is equal to 1 half. Now that we are done solving for values of a and b, we can now proceed to the integration process. So it is in this part that we can apply now our integration by partial fractions, because you can definitely replace now your 2 all over x squared minus 4 by the expressions a over x plus 2 plus b over x minus 2. And we are done already solving for values of a and b. So we replace a with negative 1 half, and we replace b with positive 1 half. Those are the values that we have earlier. So a is equal to negative 1 half, and b is equal to 1 half. So instead of getting the integral of 2 all over x squared minus 4 dx, we need to get the integral of negative 1 half. A is being replaced already, all over x plus 2 plus 1 half over x minus 2 dx. Okay, since your negative 1 half is in the numerator, you can actually factor that out. So you have negative 1 half times the integral of dx all over x plus 2 plus 1 half times the integral of dx over x minus 2. You learned earlier that in getting the integral of expressions in this form, you need to apply substitution. So you let u sub 1 be equal to x plus 2, and then you get the derivative of u sub 1. We'll be using two variables here, u sub 1 and u sub 2. So the derivative of u sub 1 is equal to dx. And on the other side, you'll be using u sub 2 and equate that to x minus 2. So du sub 2 is equal to dx. You get the derivative. Then now we replace your dx with du sub 1. So that's the reason why you have here negative 1 half times the integral of du sub 1 over u sub 1 plus 1 half times the integral of du sub 2 over u sub 2. Now, you've learned in our previous lesson that whenever you have an expression of this form, the integral is the natural logarithmic function of u sub 1. So here, the integral is negative 1 half times ln of the absolute value of u sub 1 plus 1 half times ln of the absolute value of u sub 2, okay, plus the arbitrary constant c. Okay, if you can still remember, if you're asked to find the integral of dx all over x, the result is ln of the absolute value of x plus c. So you apply the process here. Okay, but of course, previously we have expressions that can be substituted by u sub 1, and here we're going to replace u sub 1 by the original expression, that is x plus 2. So our final answer therefore is negative 1 half ln of the absolute value of x plus 2, and we replace also your u sub 2 here by the original expression, that is x minus 2. So you have here plus 1 half times ln of the absolute value of x minus 2 plus the arbitrary constancy. So that's the integral already of our function, uh, integral of 2 all over x squared minus 4 dx using integration by partial fractions. Okay, let's proceed to the second example. Here, we apply the same process. So if we are asked to find the integral of 5 over x squared minus 3x dx, you need to think of the factors of the denominator first. So in this case, the factors are x and x minus 3. So you have 5 over x squared minus 3x, and this is definitely equal to a all over x plus b over x minus 3. We add the dissimilar rational expressions. So you have here 5 over x squared minus 3x, and this is definitely equal to, the least common denominator is x times x minus 3. You divide x times x minus 3 by x. The answer is x minus 3. Then you multiply that by a. So we have here a times x minus 3. And that that is actually being applied on the second expression. So you have b times x here. Then you're aware that the denominators of the left and the right side of the equation are equal. Therefore, we can now equate the numerators. So 5 is equal to a times the quantity of x minus 3 plus b times x. And then again, we think of a number that will make your second expression equal to 0, and that is x is equal to 0. So we substitute the value of x in our equation. You have 5 is equal to a times the quantity of 0 minus 3. Your x here is being replaced by 0 already. Plus b times, of course, the value that is being mentioned earlier, that is 0. So your b times 0 will give you 0. Definitely, you're left with the equation 5 is equal to negative 3 times a. So your a here, therefore, is negative 5 over 3. And then for the value of b, you think of a number that will make the first expression, a times x minus 3, be equal to 0. So in this case, our x is equal to 3. So you have 5, and this is equal to a times 0. Okay, that's 3 minus 3 plus b times 3, that is equal to 3b. So your b now here is 5 all over 5 over 3. Okay, so your integral of 5 over x squared minus 3x dx can then be equal to the integral of a over x plus b over x minus 3 dx, and we are done solving for the values of a and b. So we can now replace your a with negative 5 thirds, and then your b with 5 thirds. So we have the integral of negative 5 thirds over x dx plus 5 over 3 all over x minus 3 dx. So in this case, we can factor out negative 5 over 3 times the integral of dx all over x. And on the other side, you have 5 over 3 times the integral of dx all over x minus 3. So the answer therefore here is negative 5 over 3. You're aware that the integral of dx all over x is ln of x, the absolute value of x, plus 5 thirds times ln of the absolute value of x minus 3 plus the arbitrary constant c. Now, you look at the third example. Here, you can actually you can actually see in this example that there are some cases wherein the values of A and B do not only differ by the sign, but instead we can have two separate values for A and B. Okay, so if you notice here in our previous examples, the only difference between the values of value of A and B are the sign. So, for this example, A here is negative 5 over 3 and B is 5 thirds. So the difference is the sign. But you can see here in example number 3 that our A and B can have distinct values other than the condition that I mentioned earlier. So, for example, if you're asked to find the integral of 3x squared over x squared minus x minus 6dx, of course, we do the process of decomposition. You have 3x squared over x squared minus x minus 6, and this is definitely equal to a over x plus 2 because the factors of x squared minus x minus 6 are x plus 2 and x minus 3. So you have 3x squared over x squared minus x minus 6 is equal to a over x plus 2 plus b over x minus 3. So you have the equation 3x squared over x squared minus x minus 6, and this is equal to a times the quantity of x minus 3 plus b times the quantity of x plus 2 all over x plus 2 times x minus 3. We are adding actually these two dissimilar rational expressions. Okay, so we can now equate your numerators. 3x squared is equal to a times x minus 3 plus b times x plus 2 because the denominators are the same. And again, applying the process that I mentioned earlier in our previous examples, you think of a number that will make the second expression be equal to 0. So in this case, our x is negative 2. So you substitute the value. You have 3 times the quantity of negative 2 raised to the second power. And this is definitely equal to a times negative 2 minus 3 plus b times negative 2 plus 2. Definitely the second expression will now be equal to 0. So you are left with negative 5a, and that is equal to 12. Our a, therefore, is negative 12 over 5. Now, for the second value, you need to think of a number that will make the first expression be equal to 0. So in this case, your x is equal to 3. So you have 3 times 3 raised to the second power. This is equal to a times the quantity of 3 minus 3, which is 0, plus b times the quantity of 3 plus 2. So you have the equation 27 is equal to 5b. So in this case, your b is equal to 27 over 5. We now have the values of a and b. So in our next step, we are now ready to solve for the integral of the function. So the integral of the function 3x squared over x squared minus x minus 60x therefore is equal to the integral of the value of a is negative 12 over 5. So we replace a by that value here, negative 12 over 5 all over x plus 2 dx plus the integral of 27 over 5 all over x minus 3 dx. So in that case, we can now factor out the constants. So you have negative 12 over 5 times the integral of dx over x plus 2 plus 27 over 5 times the integral of dx over x minus 3. So the usual process is that in getting the integral of these functions, you need to apply substitution method. But in our first example, I have shown to you the process of getting the integral of similar functions using substitution. So we can now directly go to its integral. So negative 12 over 5, the integral therefore of dx all over x plus 2 is ln of x plus 2, and the integral of dx over x minus 3 is ln of the absolute value of x minus 3. So the answer therefore to our problem, integral of 3x squared over x squared minus x minus 6 dx is equal to negative 12 over 5 ln of the absolute value of x plus 2 plus 27 over 5 ln of the absolute value of x minus 3 plus the arbitrary constant c. Okay, so that ends our discussion this morning. I hope you learned something today. Goodbye.